I'm Tiffany.
I'm Madeline.
And I'm Nathan.
And today we are going to talk about gravity and its relation to our planet. Have you ever wondered why we don't float on Earth like we would on the moon? Probably not, but we're going to tell you anyways. It's this funny thing we like to call gravity. A long time ago in a galaxy far, far away. Just kidding. A school guy named Isaac Newton discovered the gravitational constant that will be featured later. Today, we're going to be focusing on the equation for gravitational acceleration. The gravity of the planet is equal to g, the gravitational constant, times the mass of the planet over the planet's radius squared, which is a mouthful, I know, but we'll come back to it later. Before that, we want to give you a flashback to your childhood to give a little bit more insight onto this topic. Hit the clip.
Come along, class!
Hey! I feel like I weigh the same here as I do on Earth.
That's because Venus is about the same size as Earth and has about the same gravity.
Come on, Arnold.
Now you're probably wondering, so what? Well, I'm afraid to say that Miss Frizzle didn't tell you the whole truth. The truth is that the gravitational acceleration of a planet is actually caused by the mass and the size of the planet, not just the size as stated in the video.
We can prove this using the equation for gravitational acceleration. Little g equals big G times m over r squared, where little g is the gravitational acceleration of our planet and big G is the universal gravitational constant. To give an example of this, we will solve for the gravitational acceleration of Earth. If we take big G, 6.67 times 10 to the negative 11th newtons, times the mass of Earth, 5.9724 times 10 to the 24th kilograms, over the radius, 6,378,000 meters squared, which comes out to approximately 9.8 meters per second squared. We can now compare this to Venus by taking big G, 6.67 times 10 to the negative 11th newtons, times the mass of Venus, 4.8675 times 10 to the 24th kilograms, over the radius, 6,051,800 meters squared, which comes out to approximately 8.87 meters per second squared. If we subtract these two, we get a difference of approximately 1 meter per second squared, or a 10% difference.
This difference would be nearly unnoticeable to humans walking on Venus. Now, while this may seem accurate to the clip we watched, it is only by coincidence that Venus is also similar in size to Earth, because the mass of a planet is not merely caused by its size, but rather by its density.
So, in conclusion, the gravitational acceleration on each planet depends on its mass and radius. Although it would be easy to assume that walking on a planet would be the same anywhere in the universe, these two factors can completely change the way that the acceleration of gravity works on each planet. Whether you're walking on Earth or jumping on the moon, gravity plays a major role in every step you take. How cool is that? Of course, with this knowledge of gravity, we don't want to mislead you with the hypothetical scenario of walking on other planets in our solar system. Just like there are many factors that contribute to gravity, there are also hundreds of other factors that go into realistically visiting a planet. For example, on Venus, the average temperature is 464 degrees Celsius. This temperature alone prevents any human from even thinking about traveling to the planet. So remember, although hypothetically walking on Venus would be similar to Earth, I do not recommend visiting.
Well, guys, I'm Tiffany.
I'm Madeline.
And I'm Nathan.
Thank you so much for hanging out with us. We hope you enjoyed learning about gravity just as much as we did. Have a great science-filled rest of your day. May the science be with you. Go team! Okay. How about... Like we would on the news. Boom.
Beautiful.
One take. Hey. You know what makes my blood boil? Venus.